Okay, thank you. So I'll be talking about interactive learning, and just to set the context a little bit, one thing I should point out is something pretty obvious, which is that the usual model of supervised learning, to which we've all become thoroughly accustomed, is really very rigid. Okay, a data set is obtained, a human being is brought in to label the data, the human being goes away, and at some later point in time, a machine is started up, given this stack of labeled examples, and told to fit a classifier to it. Okay, so this is a very constrained setup. It doesn't resemble the way we learn. And an interesting question is, what are the consequences of learning in this sort of a constrained paradigm? Okay, so over the years, people have realized and on occasion proved that there are a whole bunch of fundamental limitations or hurdles to learning in this way. There are lots of concept classes that seem perfectly natural to us, like disjunctive normal form, that seem well nigh impossible to learn in this model. There are sample complexity lower bounds that tell us that we need astronomical numbers of samples to learn concepts, whereas we seem to do pretty well with much fewer examples. Because the feedback in supervised learning from humans consists only of labels, we end up with classifiers that are pretty inscrutable and are incapable of explaining their predictions, and so on and so forth. There's a whole bunch of this bad news. And one of the questions that I'm interested in is how much of this bad news is merely an artifact of the impoverished environment in which we are forcing these machines to learn. Okay? What if we move to a less restrictive scenario, a situation in which the learner can interact with a human while learning is taking place, and where the feedback from the human isn't just labels, but is richer, things like similarity judgments or simple explanations? Do some of these hurdles go away? And it certainly seems like a lot of them do. Okay, and so this is sort of the general theme that I wanted to talk about. And so what I'll do is I'll start with just a few brief examples to sort of illustrate the range of possible interactions and also the kinds of benefit that can accrue from this interaction. Okay, so I'll talk about active learning, machine teaching, and learning from simple explanations. And then I'll move on to my main topic, which is using interaction to augment unsupervised learning. Okay. So perhaps the form of interactive learning that's most familiar to all of us is the active learning of classifiers. Okay, this is a situation in which your goal is to learn a classifier, but all you have is a large amount of unlabeled data, and you don't have enough money to label all of it. You only have the wherewithal to label a few points, and the question is, which points are you going to choose? You could choose them randomly, but it turns out that a much better thing to do is to do something interactive, is to go into this loop where you adaptively label one point at a time, and you always query the point that seems roughly maximally informative given the labels you've seen so far. Okay, so this is the active learning paradigm, and I'm not going to dwell upon it because it's pretty familiar. There's been a lot of theory work on it. And one of the messages from this work is that in this case, this kind of interactive querying can lead to huge reductions in sample complexity. Okay, there are many situations in which the number of examples needed by the interactive procedure to get a classifier of a certain accuracy is only logarithmically as many as would be needed by a random querying procedure. Okay, so this is a case where interaction can break sample complexity barriers. So a related setting is machine teaching. And so in active learning, it's the learner that's trying to figure out which examples are the most informative. In the teaching setting, what happens is that there's a teacher, a benign teacher, who wants to pick a small set of examples that convey the target concept as expeditiously as possible. Okay? Now, there are many models of teaching out there, and perhaps the one that's been the most influential in machine learning circles is the model that's due to Kearns and Goldman and Shinohara and Miyano. Okay? And what they did is to introduce the notion of a teaching set. Okay? So let's say the learner has a concept class C, and the target concept is some C star in the class. A teaching set is a set of examples that are labeled according to C star and that uniquely specify C star. Okay? So the only concept in C that's consistent with all these examples is that one target concept C star. Okay? So that's a teaching set. And the goal of the teacher is to find the optimal teaching set, the smallest possible teaching set. Okay? Now, you can also generalize this to epsilon teaching sets, where the only concepts consistent with the teaching set all have error less than epsilon with respect to whatever the underlying distribution is. Okay? So this is a very nice and natural definition of teaching. And so let's look at an example. So let's say the data lies on the line, and the kind of concepts you're looking at are just thresholds on the line. To one side it's plus, to the other side it's minus, and that this is the target threshold over here. Okay? So what is the optimal teaching set? It's one example immediately to the left of the threshold with a minus label, and one example immediately to the right of the threshold with a plus label. Okay? Because if you give those two examples, it really pins down where the boundary has to be. So does that make sense? And by the way, feel free to ask questions at any point, okay? So in this case, the teaching set has the size of just 2. Okay, so it's very efficient. Okay.
So are there situations where these are really different than sample compression schemes, or are they often close?
Yeah, so it seems like this is very much motivated by, the teaching, of course, is a very broad practice. And this is a particular view of teaching that's motivated by, it's defined in terms of some sort of compression. Mm-hmm. Now, there's a related practice of sample compression where the compression scheme, where again, there's just a few examples that uniquely specify the target concept, but that is with respect to a specific algorithm of the learner. And here, no assumption is made about the learner's algorithm. Yeah.
This presumes mutually exclusion of the classes, so no instance example can belong to 2 classes.
Yeah, so this is a setting of very clean data. Okay, great. So this is a very nice model, but one big problem in it is that it only works if the teacher actually knows the learner's concept class. And this is not something that's familiar in teaching at all, So when we teach a bunch of students, we have no idea what concept class they're using. Who knows what's going on in their heads, right? And if you're teaching a machine, well, then you know what concept class it's using. You know that it's a random forest or a neural net. But that's not helpful, okay? It's not something that that's likely to influence your choice of teaching examples. So there have been a bunch of other teaching models that have been proposed, but as far as I know, they all have this feature, that you have to know the learner's concept class. And in fact, some of them go much further and say you know the learner's algorithm as well. Okay? And so to my mind, one of the fundamental questions about teaching is, can you teach somebody if you don't know what concept class they're using? Okay? Because that seems to be the real situation. So I'll describe some recent work with Daniel Su, Daniel Kane, and Jerry Zhu. And so we start by looking at a mild relaxation of the teaching framework, where the teacher doesn't know what the learner's concept class is, but has a short list. Okay? It knows that the learner's concept class is either C1 or C2 or CK, and these classes all have, say, VC dimension D and teaching set size T. Okay, so what can the teacher do in this case? So here are 2 things the teacher could do. Okay. It could give a teaching set for the union of all of these concepts. It could say, let's just look at this union concept class, give a teaching set for that, and that has potentially up to T times K examples in it, okay, which could be pretty bad. Or it could just revert to supervised learning and give D over epsilon random examples. We know that always works. Okay, so these are 2 options that the teacher has. And the first thing we showed was a negative result, saying that without interaction, this is pretty much the best you can do. Okay? So if the teacher doesn't get to talk to the learner, but just has to serve up the examples in advance, then it really can't do better than this. And in particular, as k grows, the best thing it can do is to simply provide d over epsilon random examples, okay, which is not teaching at all. Okay? But it turns out that the story is very different if interaction is allowed. Okay? So here we move to a more general setting where the teacher knows nothing at all about the learner's concept class. It doesn't have a short list, it knows nothing about it. Okay? But interaction is allowed. And the interaction proceeds in rounds. So on each round, the teacher supplies one more teaching example. The learner updates its model. Whatever model it has is consistent with the examples it's seen. And then the teacher is allowed to question the learner. Okay? It's going to probe the learner's models on a few instances. What's your label for this? What's your label for this? So if the learner is a student, this is tantamount to giving a quiz. If the learner is a machine, this is tantamount to the machine just giving you the classifier as a black box, and then you can probe it on some instances. And based on what the teacher sees, it then chooses its next learning example. It chooses its next example. And it turns out that if you do things in this way, then you can always find teaching sets of size t times d times log 1 over epsilon, which is in general a whole lot better than d over epsilon. Okay? So you can actually teach in this interactive setting. So how does this work? Let's see, is the teacher trying to figure out, maybe the teacher is trying to figure out the learner's concept class. Nah, there are just too many choices and there's too many variations. Is the teacher looking at the learner's responses and then fitting a non-parametric model to it? That's something it could potentially do, but that would require a lot of testing. Okay, so that's not what it's doing. No, the way this works is just to understand that teaching defined in this way is really just a set cover problem. Okay, the learner has a set of concepts C. Okay. And we want to eliminate all the bad concepts, everything other than C star. Each teaching example kills a bunch of concepts, eliminates a bunch of bad concepts. And a teaching set is something that eliminates all the bad concepts, covers all the bad concepts. So this is exactly a minimum set cover problem. Now, unfortunately, in this case, we don't know the concept class, so we don't know which concepts we need to cover, right? But there is an online version of the set cover problem as well. There's an online version of set cover where the elements to be covered are not known in advance, but they appear one at a time. And there's been a beautiful algorithm developed for this by Noga Alon, Niv Buchbinder, Sefi Naor, and a few other people. And it turns out that that algorithm can be simulated in this context, and that's how you get there. That's how you find it. Okay, so this is a situation where the ability to interact actually makes teaching possible, even when you don't know the learner's concept class.
Two things, maybe so I kind of lost track for a bit about what exactly will be the interaction here. And a minor question was, is there any interesting geometric constant sitting in the big O, or there's nothing interesting inside?
Yeah, there's nothing interesting in the big O. So the interaction is that on each round, the teacher provides one more example, one more teaching example that the learner has to be consistent with. And then the teacher is going to basically quiz the learner on a bunch of examples. It's like giving a test before deciding what to ask for next. Okay? Okay, so that's teaching. Another way in which interaction might be helpful is to move from labels, which are really a very rudimentary form of feedback, to richer feedback. Okay, so situations where the human labeler is not just saying plus or minus, but is providing more information. And here the fun or the challenge is to sort of quantify how this information would be provided and how to exploit it. So let me give you some examples. So suppose a human is labeling a document, okay? So they read the document and they say, okay, sports, okay? Now in the process of doing that, it's really easy for the labeler to just highlight a few words that are highly indicative of that label, you know, like batsman or goalie, okay? There's almost no extra effort involved. And something like this could be hugely useful, for example, in feature selection in some high-dimensional space. Okay? Here's another example. Let's say the human's labeling a bird. Okay? So you say what the bird is, and in addition, could just click on a part of the bird, maybe the beak, that is very useful in distinguishing that particular species from other similar species. Okay? So it's a very useful discriminating feature. Okay?
So again, just to get it straight, so here sometimes the information is more like additional knowledge in terms of features, which are now kind of being treated as, previously I had just one bit of information which was a class label, but this is not quite like I have a structured, more complex, bit complexity of the classes.
Yeah, basically the idea is this sort of the simplest form of explanation. Just, it's like, this is a sports document. Look, words like goalie and batsman and,
But mostly
wicket.
in terms of like features.
Features,
like
yeah.
Which features kind of act semantically like labels?
Which features act semantically like labels, or which features are useful in distinguishing, in resolving points of confusion.
How would you explain with hard negatives?
Sorry?
In graphics, hard negatives. When you're trying to learn, so the idea is if you have, say you want to identify if there's birds and images, and so most of the image, if you do square pieces that if you can involve squares across the image, most of the images don't, most of the examples you get don't have birds in them. So you have a whole bunch of negatives, and it's hard to choose what are the right negatives to train with. But if you train on the negatives that, if you do two training, and the first time you first train, and then you see which negative examples cool your classifier and look like positives, and then you select those to train on next time, you'll get a much better discriminator. So I'm just wondering how this example with the bird, where you have a human who's actually selecting sort of these hard negatives, would map to this sort of principle.
Yeah, so I think it's related, and so I'll just flesh this out a little bit. And I think it's very closely related. So the whole challenge here is to formalize this type of feedback. It seems really fuzzy, and to come up with algorithms that are able to exploit it. Okay, and so this is a fun thing to try out. There are really many different types of feedback like this, and I'm just going to give you one example. Okay, so let's say that the learner is trying to learn a classifier that takes an animal represented as a bunch of features, and needs to say what type of animal is it. Is it a mammal or bird or reptile, etc. Okay? So learning takes place in rounds of interaction. So at any given time, a new instance appears, say a whale represented as a list of features. Now the learner uses its current model to predict the label of this. And let's say it says fish. Okay? It thinks it's a fish, which of course is not correct. Okay? In addition, it gives an example of the kind of fish it thinks it is. Okay? So there are many different types of fish, and what the learner is actually saying is that I think whale is a fish, and I think it's the kind of fish that a shark is. Okay? So it's giving a little bit more specific information. So now the teacher, the human, gives the correct label. The human says, no, it's not a fish, it's a mammal. And moreover, here's a distinguishing feature, scales, that separates sharks from whales. Okay, whales don't have scales. Sharks have scales of some kind. Okay, believe it or not. Okay, so what this is saying is that this feature separates sharks and fish like sharks from whales and mammals like whales. Okay, so this still seems a little bit fuzzy. What are the exact semantics over here? Okay, so let me just show you a picture. There are many types of mammals. Okay, there are the common land mammals like dogs and cats. Then there are the weird ones that lay eggs like a platypus. Then there's the ones that live in the sea and so on. Okay, and so you can imagine that any of us in our mind have carved up the space of mammals into different groups. And maybe we all do it differently, who knows? Okay, we have the same concept of mammal, but perhaps we carve them up in different ways in our minds. So let's say that in the mind of the labeler, there's this kind of grouping. Okay, the labeler thinks of things in this way. Okay, so this new instant appears, whale, which is right here, a type of marine mammal. The learner thinks that it's a fish, okay? And what the human does is that, no, it's a mammal, and then provides a feature that separates this entire group from this entire group. It separates all marine mammals from all cartilaginous fish. Okay? So it provides that one distinguishing feature. Okay? So that's the setup. Now, when is it possible to provide features like this? When is it possible to give feedback of this type? Basically, when each class can be expressed as a DNF. Okay, so if you can give feedback like this, it means that, okay, if you look at this particular group, there's one feature that separates it from cartilaginous fish, another feature that separates from bony fish, another feature that separates from one kind of reptile, another feature that separates from one kind of amphibian. So basically, you can come up with a conjunction that separates this cluster from all the things that are not mammals. Okay? And basically, that means that mammals can be represented as a DNF. Okay? Now, with feedback like this, though, it's very easy to learn. And in fact, there's a very simple learning algorithm which has the following property. It's guaranteed to converge to the right concept. And if there are m groups overall, it will make at most m squared mistakes over the entire lifetime of the process. Okay? Now, ordinarily, DNF is a concept class that we consider hard to learn, okay? But that's in the standard supervised learning paradigm. And here, when you get a little bit more information, when you get slightly richer information in terms of these features, it becomes much easier, okay? And this kind of information will be natural in some contexts, not natural in others, okay? And so I think it's really interesting to sort of come up with a whole bunch of different types of feature feedback that apply in a broad range of cases. Okay, so I've just given a few examples of interaction. I've talked about machine teaching, learning from simple explanations, and hopefully these give a sense that interaction really has the potential to redefine what is efficiently learnable, to sort of reshape our view of that. But a lot of work is needed in formalizing models of interaction and coming up with algorithms that can exploit it. Okay, and so what I'll talk about for the rest of the time now is a sort of a less speculative, more fully baked use of interaction, and that is to augment unsupervised learning. Okay. So in unsupervised learning, there are no labels. You just have a large amount of raw data, and the goal is to find structure of some kind in the data, clusters or topics or embeddings and so on. Okay? Now, over the past 2 decades, there has been huge progress in algorithms for unsupervised learning. We now have algorithms for clustering, topic modeling, and so on that have strong performance guarantees that they're optimal or close to optimal in various specific senses, okay? But unfortunately, the fact of the matter is that despite being optimal, these algorithms never give you what you want, okay? And that's just a result of the fact that unsupervised learning is inherently underspecified, okay? Even if you have an optimal algorithm, okay? So, look at clustering, for example. If you're clustering people, should you cluster them by height and weight, or by how nice they look, or by their ethnicity, or by geography? These are all perfectly legitimate clusterings, and in a sufficiently high-dimensional feature space, they would all be salient. But an unsupervised algorithm has no way to magically guess which of these alternatives you want. Okay? So it doesn't matter how optimal they are, they're not going to give you what you want. And so this seems like a situation where interaction would be very useful. Okay? So how might this interaction go? Okay? So let's look at clustering, for example. Okay? So you have some machine. It's got this data set X that it's clustered. And now it wants some feedback on the clustering. How would it do that? Well, it can just hand you the clustering and say, what do you think? Is this good or bad? But this could be a clustering of 10,000 points, something enormous. Okay? So we're going to look at interactive protocols in which each round of interaction is only constant time for the human. Okay?
So for example, for the critique you gave for clustering type of things, so what about semi-supervised clustering? So would you consider that is the thing you're about to describe supposed to be reducing the label complexity of semi-supervised, or is it?
That's right. So say,
goal?
right, no, so that is exactly the same goal, right? Semi-supervised clustering, in which you have your data points, and there's a little bit of information from the user about the type of clustering they're interested in. And so the question is, can we do this in a more interactive way to really minimize the amount of interaction that's needed to converge to the right thing? That's exactly right. Okay. Right, so we'll be looking at protocols in which there are rounds of interaction, so it's adaptive, and each round is just constant time for the human. Okay? So the computer can't just show the entire clustering, but what it can do is to say, look, I've clustered 10,000 animals, and here's how it looks for these 6 animals. What do you think? Okay? And so the human takes a look at that and says, you know what, it doesn't look quite right. For example, dolphin and whale should be together. Okay, so it just gives an example of something that's wrong. The human just gives an example. So, you must link dolphin and whale. Okay? Or for hierarchical clustering. The computer says, I have this hierarchical clustering of 10,000 animals. Here's what the hierarchy looks like restricted to just these 6 animals. And the human looks at that and says, you know what? It doesn't look right to me. If I had to fix the whole thing, that would be a little tricky. I would need a pencil and paper to really work it out. But if I just have to give you one quick fix, I can tell you that there should be some subtree that contains dolphin and whale, but not zebra. Okay, so it's a triplet constraint. There should be some cluster that has dolphin and whale, but does not contain zebra. And so these triplets actually are something that are very nicely geared towards hierarchies. It's actually perfectly in sync with them. Okay, so these are examples of the kinds of interaction that I'll be talking about. And I'll describe a scheme that works for pretty arbitrary types of structures, not just clusterings, but topic models, knowledge graphs, and so on. Yeah.
Are you also going to talk about bounding the amount of interaction needed, or because it proceeds in rounds?
It proceeds in rounds. I would like to, but to be honest, I don't know yet. So that's one of the open problems. So I'll just be talking about algorithms for doing this. Okay. Yeah. Okay, so what I'll do is I'll just focus on the hierarchical clustering example, and later we'll see how this just generalizes quite nicely to more general structures. Okay, so hierarchical clustering is something that I much prefer to flat clustering. You get a view of the data at all levels of granularity. So you get this multi-scale structure. You don't have to specify the number of clusters in advance. And there are these nice algorithms like average linkage that are now part of every standard package. So it's a nice form of analysis. But like every other type of unsupervised learning, it's inherently underspecified. And so it could use some interaction to improve the quality of the final result. Okay? So what do we need to do interactive hierarchical clustering? So there are 3 things we need. We first need a method of interaction, and I've already said what that would be. On each round, the computer just displays a subtree and gets a little bit of feedback on it in the form of a triplet. We need a cost function over all possible hierarchies. And basically what we'll be doing is choosing a hierarchy by minimizing this cost function. Okay, so if we don't have any interaction, we'll just minimize the cost function. If we have some constraints, then we'll minimize the subject to constraints. Okay, and this is where we run into some trouble. Okay, because we don't actually have, so if you look at something like average linkage, which is perhaps the most popular hierarchical clustering algorithm, there's no cost function over there. It's just specified procedurally. It says do this, do this, do this, and boom, you've got a tree. Okay, so this is not good. It would be nice to have a cost function, because if we don't know what it's optimizing, how can we tell it to optimize the same thing subject to constraints? Okay, and so in order to solve the interactive version of this problem, essentially we have to solve the unsupervised version of it first. And so I'll just say a little bit about that. And then we also need to be able to optimize this cost function subject to constraints. Okay, so let's just talk briefly about the unsupervised version of hierarchical clustering. Okay, and we need a cost function for this. Okay, so no interaction going on over here. We just have a set of endpoints and we want a hierarchy on it by minimizing some cost function. Okay, and so the points might be in Euclidean space, or more generally, let's just say we have a similarity function on the points. Okay, and we can represent this by a graph where we have a node for each of the data points, and we have edges with weights representing the level of similarity. This is just an example in which all the similarities are either 0 or 1. Okay, so in general, we can represent our input as the similarity graph, where the edge weights encode similarity. And now we need a cost function over all possible hierarchies. And so one idea is, look, an edge encodes similarity. So we don't want to separate, if 1 is similar to 3, we don't want to separate them. We don't want the clustering to cut that edge. So let's just charge the clustering for every edge that it cuts. But in a hierarchy, every edge gets cut in the end. Okay? So what do we do then? Well, what we can say is that it's very bad if an edge gets cut at the top of the tree, but it's not so bad if it gets cut near the bottom of the tree. And that's the idea for the cost function. Okay, so let's look at an example. So here's the same similarity graph. And now we want a cost function that assigns a cost to every possible tree with these 6 leaves, with 6 leaves. Okay, so for example, what cost would be assigned to this tree? Let's take a look. So the first thing that this tree is doing is separating 1, 2, 3, 4 from 5, 6. So it's cutting this edge over here. So we're going to charge it 1 for cutting that edge. Now on the left, it's separating 1, 3 from 2, 4. So it's cutting these 3 edges. Okay? So we charge it 3, but at this point in time, only 2/3 of the data remain, only 4 out of 6 points. So we charge it 2/3. We have a discount factor, okay? Over here, it's separating 5 and 6, so it's cutting 1 edge, but only 2 out of the original 6 points remain. So only 1/3 of the data remains. We charge it 1/3. Okay? So in general, here's the cost function. For each edge, we charge for the edge, the similarity weight of that edge, but we weight it by the fraction of the data that remains when that edge was cut. So if there's an edge between I and j, when is that edge cut? Well, you look at the lowest common ancestor of I and j in the tree, that's when the edge got cut. How many descendants are in that subtree? Divide that by n. That's the fraction of the data that remained when the edge was broken. Okay? And that's how much we charge for the edge. Okay, so it's quite a natural cost function. And we can just do some quick properties just as a sanity check. If the original graph is disconnected, then the right thing to do is to first separate out those connected components. Okay? And the one useful property is that there might be several optimal trees, but there's always one that's binary, so we don't have to worry about the non-binary case. Let's look at a few canonical examples. So suppose the input is a line graph. What kind of tree on n points will minimize the cost? Well, let's look at a tree that looks like a caterpillar, that first separates off 1 point, then another, and then another, versus a tree that's completely balanced. In the caterpillar tree, the first edge cut is this one, for which it gets charged 1. The next edge gets charged n minus 1 over n. The next one gets charged n minus 2 over n. So the overall charge for this tree is n. For the balanced tree, the first edge cut is in the middle, for which it gets charged 1. The next 2 edges get charged 1/2. The next 4 edges get charged 1/4. And so the overall cost is log n. Okay, and so it favors the balanced tree. If the input is the complete graph, then it turns out that all trees have the same cost. Okay, so if the input is a complete graph, every pair of points is equally similar, then it's really not favoring any kind of cluster structure, and all trees end up having the same cost. Okay? And if the input graph is generated by a planted partition model, then it's also easy to show that this is the right thing in expectation and with high probability. Okay? So it's a reasonable cost function, but now we need an algorithm to minimize it. And it turns out that unfortunately this is NP-hard. Like all clustering, k-means, k-center, they're all NP-hard, and this is no different. And so we have to come up with a heuristic. Okay, so how are we going to do that? Well, we have this similarity graph. Let's just, what if we just use spectral partitioning to divide it in 2? And that's going to be the top split, and then we recurse. Okay, that seems like a simple algorithm. So let's write that down. So at each stage, we do spectral partitioning or some other kind of sparse cut approximation. And then we recurse on the two sides. Now, sparse cut is again a problem that we cannot optimally solve, but there are all sorts of approximation algorithms for it. So let's say we use an alpha approximation to sparse cut, and we recursively build a tree in this way. It turns out that this is an alpha log n approximation to the optimal tree. Okay, so this simple algorithm gives you an alpha log n approximation. And actually, this is what I was initially able to show. But shortly thereafter, various other people, Moses Charikar, Vagos Chatsiafriatis, Varun Kanade, Claire Mathieu, and some other people showed that actually this algorithm achieves just an order alpha approximation. It's like 6 alpha. Okay, so there's a nice approximation algorithm for this cost function hierarchical clustering. And so let me show you an example. Here, I ran it on the animals with attributes data set. So this contains a bunch of, I think, 85 animals. And for each animal, there are 50 features. Okay? And this is the clustering you get. And by using that spectral partitioning algorithm. And it looks pretty good, look, seal, killer whale, dolphin, hopping, some marine stuff on the top, chimpanzee and gorilla. It looks good to me. But, in standard unsupervised learning style, it's pretty decent, but it's not right. Okay? There's a lot of things that need to be fixed, for this to pass muster with the biologists. Okay? And so that's when we begin rounds of interaction. So on each round, a random subset of the tree is shown. Okay? And so the expert either accepts this or fixes some part of this. And this frankly looks really good to me, but this is not correct. Okay, there are apparently a lot of mistakes here. Yeah.
So because it's happening in rounds, okay, so it makes sense that at each round you pick some random subset, but wouldn't you actually want to more cleverly select the subset displayed in a given round?
Yeah, you would, and in fact, this is a relatively small example. So picking random subsets works just fine over here, and in fact, it converges to the right tree in just a few rounds. Okay, but in bigger examples, you'd want to pick it more intelligently, and I'll get to that. Okay, and so that's what we had to do. Yeah, so over here, the expert looks at that, provides a fix, and then it gets incorporated. Okay, and the main thing to kind of point out over here is that each fix seems to only refer to 3 animals, but because of the loss function, it gets globally propagated. Okay, so it's not just a local.
How do you incorporate a constraint like this? So how would you fix the tree?
Right, so there's several. So depending on how that loss function is optimized, so there are actually ways of. So the people who've been dealing with these kind of constraints for a while are the computational biologists who work on phylogeny, and they have a bunch of nice ways of incorporating these that play nicely with the scheme I described earlier. Another thing you can do is, so some people have also suggested a linear programming relaxation for that cost function, and it turns out that these constraints can be very easily incorporated into that. So there are various ways to do that, but what's not known is what the approximation factor is of the constraint problem.
And also, that linear programming relaxation means that you have to resolve the whole LP, or you can warm start it to just rebalance or rechange the subpartment.
I was assuming one would have to resolve the whole LP, but now that you mentioned that, yeah, if there were a way of doing that, that would obviously be much better. Right. Okay. Okay, so that's a simple procedure for interactive hierarchical clustering. Okay, and so what I want to do now is to just generalize it to talk about just to basically point out that really it's just an example of this more general framework that I've been calling interactive structure learning. Okay, and so in an interactive structure learning problem, it's an abstract problem. You have a space of instances. These could be a bunch of points you want to cluster, or a bunch of points on which you want to obtain a distance function, or an input space for a classifier, or a bunch of items on which you want to build a knowledge graph. Okay? So that's the space of instances. And we want to learn a structure over this space chosen from some set G. This could be all clusterings of X, classifiers on X, knowledge graphs on X, and so on. And there's some target G star, okay, that we want to get to. And we're going to use interaction to help us get there. And ideally, we don't want to have to use too much interaction. Okay. So what do we need? Well, in the absence of any interaction, the way we would choose a structure is just by minimizing some loss function. Okay, so if it's clusterings, it could be the k-means cost function. For hierarchies, it could be our cost function. Or you could go Bayesian and just have a prior distribution over structures. Okay. Okay. And so there'll be rounds of interaction in which we keep getting feedback. Okay. And the form of the feedback is a direct generalization of the hierarchical clustering case. Okay. So on each round, the machine has its current best guess at what the structure should be, and it wants feedback on that. Now, the structure is usually far too large to be fathomed in its entirety. So the machine can't just hand it over and say, do you like this knowledge graph or not? But instead, it displays just a constant size snapshot of it. And this is, something that, can be just about anything, just something constant size. And then the human expert looks at that and says, I like it, or fixes some piece of it, okay? And what this means is each snapshot can be decomposed into atomic pieces that are individually fixable. Okay, so I'm going to leave these things pretty hazy, snapshots and atomic pieces, but hopefully the intuition is clear and it's something that's quite easy to formalize. So this is the overall protocol. There are rounds of interaction. The learner always selects the structure that minimizes the cost function subject to these constraints that it's obtained so far. Okay? And the way it obtains constraints is that it shows a small snapshot of its current structure. The expert either accepts it or corrects a little piece of it. Okay? And the little correction forms another constraint. Okay. So one of the things, this is a pretty natural procedure, but one of the things that's going on over here is that the input from the user consists of these partial corrections. And this is something that seems fairly natural from a human interface point of view, but it's not something that I've really seen formalized in sort of statistical theory. And so I just want to say a few words about that. Okay, so what is this? So partial correction. It's a different kind of feedback. Okay, so for example, the machine might display how it would want to parse a sentence. Now, if that parse tree is correct, the user just clicks yes, which is nice. Doesn't have to type in a parse tree. Okay? Or it could display a little piece of its current knowledge graph. And there might be parts of it that the user is unsure about. I'm not sure whether this is correct or not. I'd have to look that up. But this, I'm sure, is wrong. And if that's the case, they can just point this out, and they don't have to deal with the rest. So it's convenient in that way. Or the snapshot could be a small set of instances like this, in which case the user might just pick out the flaw that's the most glaring. Says, oh, this is not a canary, but oh my goodness, this isn't even an amphibian, so I'm going to point out this one. Okay? And so there are many ways in which this sort of partial correction paradigm might be helpful. Okay? But it turns out that it does pose some problems in terms of generalization bounds. Okay, and so I'm just going to talk briefly about that in terms of the generalization theory of this kind of feedback. Okay, so the main question is, how do we select these snapshots? Are they chosen at random? Like, do we choose a subtree at random from the entire hierarchy, or is it picked in some intelligent way? And let's look at these two cases. Okay, so if, let's say, the subtree is picked at random, okay? So the user gets to see a random subset of the tree and then supplies a triplet. The triplets obtained in this way are not IID from any distribution, okay? And so the question is, can one actually learn from these? Can one come up with statistical generalization bounds for this kind of feedback? Is it possible, for example, for the learner for the human to systematically avoid certain parts of triplet space, to stay away from those and just derail convergence altogether? And this turns out to be kind of a tricky issue. But in recent work with Mike Luby, we figured out that that actually the user can't do this. Okay, there's no way, no matter how adversarially the user decides which part of this to correct, you can give statistical generalization bounds on the result. Okay, and okay, so I won't have time to go into that.
What about the converse of this? Doesn't this suggest that if the user is being benign and trying to help a lot, that helping will not really go too far either? Or?
No, so helping should go quite far, but it should, right? But it turns out that if you just look at some simple examples, the ways that occur to us to help are often not that helpful from the computer's point of view. There are different policies that would be much more helpful. So sort of, let me give you an example, right? Suppose we try to teach a classifier like cats, or like cats versus dogs, right? What are the kind of examples we like to give? Stuff like Hello Kitty, the canonical cat, right? Whereas from the computer's point of view, it might be more helpful to have cats that are nearer the boundary. A cat that kind of looks like a dog. But that's not what would occur to us. So sometimes there's this kind of mismatch between what we'd consider a useful example and what is actually useful from the point of view of the learning process. Okay. So so we also so Suvrit asked about more intelligent querying, and this is a natural thing to do. Instead of choosing snapshots at random, what if you pick them in an intelligent way? And a natural way to do this is to try and generalize active learning algorithms. And there's a lot of active learning algorithms out there. Some of them are heuristics that just have horrible statistical properties, and even though they occasionally work well, okay, I want to stay away from those. And then there are some that have these beautiful theoretical guarantees, but are just a disaster in practice. Okay, so one particular scheme that's kind of a nice balance is the query by committee algorithm. That's actually one of the oldest active learning algorithms. It's due to Sebastian Sung, Chaim Sompolinsky, and Tali Tishby from the early 90s. Okay, and it turns out that active learning algorithm, that's designed for binary classifiers, can easily be generalized to this structured learning setting. And what's more, the original algorithm didn't deal with any noise in the feedback, but you can actually change it to accommodate noise as well. And it's something very simple, and it requires a prior distribution over structures rather than a loss function. Okay, and I can show you some examples where we use this for hierarchical clustering. Okay. So in order to use this, you need a prior distribution over all hierarchies. And one nice distribution is the Dirichlet diffusion tree of Radford-Neal. Okay? And so what you would normally do is to run this random walk for a whole bunch of steps and then just take the tree that it gives you. But now what we do is that every 100 steps of the random walk, we query the user for another triplet. And we keep going in this way. Okay, and we choose this snapshot intelligently according to this structural QBC algorithm. And so here are some results for 20 news groups, okay? So over here there's the optimal tree for this data set. This is actually a classification data set, so we mean that the optimal tree is just the division into classes. Average linkage gives a tree that's really far from optimal. Its distance from optimal is 0.6. And this distance is the fraction of triplets on which there's disagreement. If you run the Dirichlet diffusion tree by itself, this is the unsupervised learning algorithm, it starts off far from optimal and it remains far from optimal. The random walk is not improving distance to optimal, but all the querying schemes help, and the intelligent querying scheme does especially well. Okay, it converges nicely to the optimal tree, and then we observe this over a bunch of data sets. Okay, so I'm not going to put this up for much longer. So yeah.
What was the x-axis?
Right, the number of iterations of this random walk, so we're running this sampler, and every, I think, 100 iterations or something like that, we ask for another constraint. Okay, and so the unsupervised thing remains far from the target, and all the interactive methods get close to the target fairly quickly. Okay, so so interactive learning has a huge bunch of different problems, and currently they really seem like disjoint problems for which people are developing one-off systems that don't necessarily generalize. But I think that there's a lot of fun work to be done here in sort of grouping these problems according to the specific algorithmic and statistical challenges that they embody, and sort of studying them at that level of abstraction. Okay, so that's the... Okay, and so I'd just like to thank my co-authors, who are the people in red over here. Okay, thank you. Okay.
Thanks, Sanjoy, for a very interesting talk. There's definitely time for a few questions.
So how do you, could this be applied to incremental learning? Kids learn example by example by example, and you want to correct them as they go, maybe, but does that work in that notion?
To correct, right. And so that sounds a little bit like the teaching framework that I was talking about initially, where the teacher provides occasional corrective feedback to the student, but doesn't want to provide too much correction. So, but wants to choose feedback that's really effective. Yeah.
A couple slides back, there was a graph that showed the improvement in performance with iterations. This one, so where it crosses average language, is that around 10,000 iterations? Does that mean that, I apologize for misinterpreting, but does that mean 10,000 times a human has to interact with the system?
No, so this is 10,000 steps of the random walk. And I think a query is made every maybe 100 steps. Let me just see. I forget what the exact, I must have written, yes, every 100 steps a query is made.
So that would be 100 interactions?
Yeah, so 100 triplets, that's right.
Okay, and did you all run this in practice? I was just wondering, because for practical purposes, I was just wondering about how long someone would interact with the system to sort of get the baseline performance.
Oh, I see. You mean how long did it take to, yeah, just to get baseline performance, it required 100 triplets, right? Just to get to average linkage level. Yeah, this is something that you'd do if you really cared about the data, and you saw the tree average linkage was giving you, or that this cost function was giving you, and you just wanted to make it better.
Right. I guess I was thinking, so this is MNIST, which is 60,000 images. I was imagining a data set that's like 10 million images, or maybe not images, but just data points. Then do you see, there might be a good way to think about that, I just don't know how, choosing, even using query by committee, to choose the right, if you only show a snapshot of, say, 20 links, and it's among 10 million, then how do you get this right so that you can efficiently run this in practice?
Yeah, any kind, currently, hierarchical clustering of large data sets is, there aren't, we don't know how to do it efficiently, okay? Average linkage is n squared. With the cost function I presented, there is the potential of doing it in time n log n. Perhaps if you use some sort of quick and dirty spectral partitioning for each individual cut, then you could potentially do it much faster than that. But this particular scheme requires sampling from this prior distribution, the Dirichlet diffusion tree, and that is super inefficient. So that's, yeah.